Hi, in today's video, we will talk about WASSCE 2021 Physics Practical, and our focus will be on question number 3, which is under electricity. This video is the part 4 of our series on the 2021 Physics Practical for Waec. So if you haven't watched the first 3 parts, I would advise you to check them out. So let's take a look at the apparatus for this experiment. You'll be given an accumulator or 2 dry cells. You'll be given an ammeter. You will also be given a crocodile clip or a jockey, which is also feasible in this case. You'll be given a 2 ohm resistor. You'll be given a key, a Constantine wire whose length is about 1 meter long. Then you'll be given connecting wires. So the first thing we need to take a look at is the circuit diagram of this experiment. Then I'll show you how to set it up. Then we'll talk about the relationship between the variables that you'll be expected to plot. Then finally, we're going to perform the experiment. So let's start with the circuit diagram. The diagram on the left is the circuit diagram, while the diagram on the right is a diagram showing how to connect the apparatus that will be given to you. So let's take a look at the diagram on the right. The diagram on the right shows a standard resistor. We've got ammeter, we've got a battery, we've got our ammeter, the plug key, connecting wires, potentiometer wire. The potentiometer wire is the same as the Constantine wire because the potentiometer is just a Constantine wire on a meter rule. So that's basically what it is here. Then the jockey I'm using the jockey in place of the crocodile clip. They are essentially they are very similar, so you can interchange them just to complete the circuit. So now let's take a look at the circuit on the left. The circuit on the left shows the symbol representing the setup. So here we have our EMF, which is the battery. We have the symbol for the ammeter. We have the symbol for the key. We have the symbol for the 2 ohm resistor. We have this line XY representing the potentiometer wire or the Constantine wire. Then the J is the jockey or the crocodile clip. So the first thing I want to do is to talk about what you be expected to measure and how your table will look like. So this is how the table is going to look like. You'll be expected to change the value of x. So x is the distance between x, capital letter X and capital letter C. That's x. Then for every given value of x, so let's say the value is from 25, let's say to 40, then let's say we have 55 and so on. For each value of x, which is in centimeter, you'll be expected to measure to take a reading of the ammeter reading. So in other words, you'll be expected to take the reading of I. So I is the ammeter reading, and that is in ampere. So this is what you'll be expected to do, and eventually you'll be expected to calculate the inverse of x, so which is centimeter raised to power minus 1. So this is going to be your table of reading. This is how it's going to look like. So for every value of x, we'll measure the current on the ammeter, then we'll take the reciprocal or the inverse of x. So the question now is, what are we going to be plotting against what? So the plot is going to be like this. You may be asked to plot I on the y-axis against x on the x-axis. So this is against x minus 1 rather on the x-axis. So this is going to be the kind of graph you'll be expecting. So the next question is, what is the relationship between I and x raised to the power minus 1. So can we derive a mathematical equation that we can use to determine I given that we know x? So let's take a look at how we can derive it. To derive the relationship between I and x raised to the power minus 1, we're going to start by determining the equivalent resistance at the top here. Then here we have the EMF, then the ammeter, and then we have the key. So let's just close this circuit. So this is the equivalent resistance of the standard resistor and the resistance from the Constantine wire. So this is how you should think about it. So the RE is equivalent to these two parts. So let's assume this to be R. Then let's take this to be RW. That's the resistance from the wire. Then let's combine them. So it means RE is equivalent to the combination of this resistance in parallel. So how can we represent RE in terms of R and RW? So we can do that as follows. 1 over R, since they are connected in parallel, is equal to 1 over R plus 1 over RW. Or you can write it this way, plus 1 over R. So now that we can represent RE as a function of 1 over RW and 1 over R, the next thing is, how do we combine I? I is the current reading on this ammeter. So what's the relationship between I, E, and RE? So the relationship here is E is equal to I into brackets R plus small r. This small r, RE plus small r, this capital letter, this small letter r is internal resistance. But we are going to assume that the internal resistance is very close to 0. So this means RE is equal to IRE. If you make I the subject, you're going to get I equals E over RE. So what's the next thing we can do here? We can write R in terms of RW and R. So this means we can say that I is equal to E times 1 over RW plus 1 over R. So this we can write as E over RW plus 1 over plus E over R. Let's take a look at the next page. We already know that I is equal to E over RW plus E over R. So then, what is RW? How can we write RW in terms of X? RW is the resistance of the Constantine wire, right? And the resistance of a wire is equal to the resistivity of that wire times the length of the wire divided by the cross-sectional area of that wire, just the cross-sectional area of the wire. So it means we can say that 1 over RW is equal to A over rho, which is the resistivity, times the length of the wire, which is x. So if we substitute 1 over r in this equation, it means I will be equal to E A over rho x plus E over r. So we can write it this way: EA over rho times x raised to power minus 1 plus ER. So what can we deduce from this equation? So we can deduce that I is proportional to x raised to power minus 1. Then the slope is going to be roughly E times A divided by the resistivity of the wire. Then the y-intercept is equal to E over R. So this is how the graph is going to look like. So the y-intercept is E over R. So if this happens to be E over R, it means the line of best fit will cross this point. So we should be expecting a graph of this kind, where the slope is EA divided by resistivity of the wire. So this is the kind of experiment where you can't easily predict the values of I given X. So the only way you can predict is if you know the value of the resistivity of the wire and if you measure the cross-sectional area of the wire. So if you can't get those two values, you can't predict the slope upfront. Okay, so let's take a look at how we can calculate R. From what we've derived, we can estimate value of R. R will be equal to E over C, where C is the y-intercept. So this can help you to check if your reading is accurate or reasonable. You just divide the EMF, which happens to be 3, by the y-intercept. If you do that and you got 2, which happens to be the resistance, the standard resistance, then that means your reading is reasonable. Or if it's close to 2, it means your reading is reasonable. So just note this formula. You might need to use it to validate your reading. So now that we've derived the relationship between I and x raised to the power of minus 1, the next step is to simulate this experiment using Mavinhub Physics Lab. So let's take a look. To perform experiments in Mavinhub Physics Lab, you click on the experiment icon, and in this case, we are performing an electricity experiment. So click on electricity, then we select the experiment we want to take. So in this case, we're interested in experiment 7, so which aligns with what we are doing. Okay, so this is the circuit diagram as discussed earlier. This is how you connect the apparatus. Then this is the apparatus given to you. Then we have the procedure. So the procedure is very straightforward. You connect the circuit, you let the jockey make contact with the potentiometer wire, you close the key and you take reading on the ammeter. Then once you've done that, you evaluate x raised to the power of minus 1. That's the inverse of x. Then you repeat the procedure for various values of x. Then you tabulate all your readings. Then finally, you plot a graph of I on the vertical axis against x raised to the power of minus 1. Then you determine the slope and y-intercept. So there are certain precautions you need to take note of during this experiment. The first is to ensure that the wires are tightly connected. So that's a very important thing to note. Then the second precaution is to make sure you remove the key after taking each reading in order to avoid draining the batteries. If you don't remove the key after taking readings, you may end up having lower voltages coming out of your battery for subsequent readings. Then the next apparatus is to ensure that error due to parallax is avoided when taking readings from ammeter. Then also ensure that zero error of ammeter is noted and taken into account. So zero error is a kind of error where your ammeter is not exactly at zero when the circuit is not connected. So let's say the ammeter is reading 0.1 without circuit being connected to it. It means whatever you're going to get, you should subtract that 0.1 from any reading you take because your reading did not start from zero. So then the last reading applies to jockey, but in this case we are using crocodile. The last error is for jockey, but in this case we are using crocodile clip, which means you don't need to worry about the last precaution. Then another thing you should note is when stating precautions, you should state it as a reported speech because you did the experiment and you should state it in a reported speech and you should use past tense like I ensured that the wires were tightly connected. So the next thing we're going to do is to make our settings to align with what Waec is going to uh, give set for you. Okay, so in this case, the voltage or the EMF is 3 volts. So I'm going to retain this as 3 volts. But then I'm going to use a different resistance here just for the sake of this experiment. So I'm going to use an internal resistance of 0.4. Then I'm going to use a diameter. Let's assume the diameter of the wire is 0.25. Then that's all. Then we're going to make this reading to be between 25 and 45 with a step of 15. So that's basically all. For those of you that already have Mavinhub Physics Lab installed, you can change the setting however you want and you will get different reading. That's the whole essence of Mavinhub Physics Lab, to enable you to explore physics under various conditions. So let's set this to be 40 minutes. Okay, then we go to the setup and we get started. So this is the simulation environment for this experiment. So the first thing I note is you need to, the switch, the key is already removed, which means before the current can flow, you need to click on this switch to allow current to flow. It's just equivalent to you removing and inserting the key. So it's very important to turn it off, in other words, to remove the key while you are not taking reading. Once you want to take reading, then you turn it on and you take your reading. Then this X value will enable you to position the jockey or the crocodile clip at different points on the potentiometer wire. So if you take it up, it means you are increasing the value of X, which means you are going to increase the resistance that the wire is contributing to the circuit. If you take it down, then the resistance that the wire is contributing will reduce. Okay, so let's take a look at the readings table. In the here you have X for 25 up to 85. Then you have your reading from your ammeter. Then you have the inverse of X. So let's take the first reading. For the first reading, X is 25. So that means we are going to set X to be 25, and which happens to be this. Then the next thing we do is to switch, is to turn on is to close the circuit by inserting the key. Then once you do that, current flows. The next step is to take readings. To take readings, you need to click the magnifier in this case and carefully look at where the ammeter is pointing. So in this case, the ammeter is almost at 2. So we can say roughly 1 point, let's say 99, something like that. It's almost at 2, but not exactly at 2. So we can say the reading is 1.99. Then the inverse of x, that is 1 over 25, is 0.04. So let's look at the second reading at x equal to 40. So the first thing we do is to turn off the switch to prevent your battery from draining. Then you move this to 40. And once you are done, you switch it on and you take reading. So in this case, we have our reading at, this is very close to, is in between 1.7 and 1.8. So we can take this as 1.75. So you switch, you remove the key, and you take your reading. So this is 1.75. 1.75. Then the reciprocal of x is 1 over 40, and that will give 0.025. The next is to take readings for when x is 55, and that will give us, let's move this to 55. Then we turn on the switch, then we'll take reading. So the value is at, if you check closely, this is 1.6. So you turn off you remove the key, then you take your reading. That's 1.6. Then you look for the inverse of x, which is 1 over 55, and that will give us 0.018. The next is when x is 70. So we move this to 70, the x to 70, then we insert the key, and then we take measurement. The ammeter reading is 1.55. Then we remove the key and we take the reading 1.55. Then 1 over x will give 0.014. So the last reading is when x is equal to 85. So we move this to 85, and then we turn on the switch, in other words, we insert the key, and we take reading. So the reading in this case is about 1.5. Now you remove the key and you record 1.5. Then 1 over 85 will give you 0.012. So now we are done with the taking of readings. So the next step is to plot a graph of I on the y-axis against 1 over x on the x-axis. So let's move on to the graph section. So to make a good graph, the first thing I want to do is to define the x-axis, the x label, the y label, and the title of the graph. So let's start with that. So the title of this graph is a graph of I versus 1 over x. On the x-axis, we have 1 over x, then we have our units as centimeter raised to the power 1, raised to the power minus 1. Then on the y-axis, we have I, that's current, then the unit is ampere, whose symbol is A. Now we've defined the axis, labels, and the title. The next thing is to determine the scale. If you want to know how to make a good scale, watch our video on how to make a graph. So in this particular instance, the scale for the on the x-axis is minus 0.005. Then the step is 0.005. Then we have the maximum to be 0.04. Since our maximum is 0.04, we need to create leave an extra space. So it means we're going to stop at 0.045. So the next is to determine the scale of the y-axis. The scale on the y-axis is a step of 0.5. So we're going to start from, let's say, 0 minus 0.5. Then we end at a value close to the maximum. Since the maximum is about 2, so we're going to end at 2.5. So this is the scale we are going to use. So the next is to get the points on our table, to get them on the graph. And that can be achieved on this application by clicking on this icon. Then we determine the point at when 1 over x is 0.04, I is about 2. So that value is going to be located at where this is 0.04 and where I is 2. So very, very close to this. So the next is when 1 over x is 0.025 and this is where 0.025 is, then I is 1.75. Then when 1 over x is 0.018, so 0.018 is very close to 0.15 and it's also close to 0.02, so which means it's somewhere here. So we have 0.018 here. Then that's at that point I is 1.6. So the next is when 1 over x is 0.014. So this is 0.014. I is 1.55 at that point. So this is 1.5 and 1.55 is somewhere here. When 1 over x is 0.012, I is 1.5. So the next thing we want to do is to get the line of best fit. So to do that on this application, you click on this icon, this graph line icon, then you'll find a line that connects as many points as possible or that runs through as many points as possible. So you can use your ruler to try out different lines until you get the right line that gives that touches as many points as possible or that is as close as many points as possible. So in this case, I think this is as close as possible to a lot of points. So I'm going to click. So this is my line of best fit. So the next is to determine the slope. To get the slope, you need to pick 2 points on your line of best fit. So I'm going to pick this point, and I'm going to pick this point. So from these 2 points, I will determine my slope as follows. So this first point is point 1. This other point is point 2. So at point 1, I is 1.5. That is, the value on the y-axis is 1.5. Then the value on the second point, value of I at the second point is very close to 1.8. So I'm going to say 1.82, roughly 1.82. Then the difference is 0.32. Then the next thing you want to do is to determine the value on the x-axis. So at the first point, the x1 is very close to 1.15. So that means we have 0.0115. Then for the second point, the value is 0.03. 0.03. If you take the difference between 0.03 and 0.0115, you will get 0.0185. So now let's calculate the slope. The slope is change in y divided by change in x. So the slope is 0.3, so divided by 0.0185, which is equal to 17.3. So for the y-intercept, you determine that by looking at the value where the line of best fit crosses the y-axis, and that value is at 1.3. So we can say the y-intercept is 1.3. So now we are done with the graph. So the next aspect is the question section. Why we ask you questions after your graph? So this is one of the likely questions you may be asked. So you may be asked to calculate the value of R naught given E and C. E is the EMF, which is 3. S is the slope from your graph, while C is the y-intercept. So we're going to use C, which is the y-intercept. So the y-intercept in this case is 1.3. So E is 3 divided by 1.3, and that will give 2.3. So the R naught here is 2.3, but we know theoretically that it's supposed to be 2. But that's what the experiment is all about. You're not expected to get exactly the same thing because we have other factors that contributed to this result, like the internal resistance that we ignored and many other factors. So let's take a look at the second question. For the second question, I'm going to skip that. You can take a look at it, solve it, and after submitting, I'll show you the correction for you to check if you got it right. So now I'm going to submit. This is the result of the experiment. The readings up seems to be okay. The graph axis seems not to be okay. I'm going to explain the reason. Then the graph points very okay. The lines and the slope and the intercept. Then the question not other okay, which I will explain. Now you should note that a large chunk of your mark will come from your graph. So ensure that you spend good time on your graph and you do a very good work, because your graph will determine your score ultimately. So let's take a look at the readings. So we got the readings right for the most part. Then this is my graph and this is the computer graph. So the reason why my graph axis score was not well graded because I used tiny spacing here. I used tiny spacing here because I assumed that my graph should have about 8 or 9 or 10 divisions. So, but in this case, the software expects me to use very small spacing. So, but in real world, your spacing should be based on the number of divisions in your graph. So if you have a lot of spacing, then you should make your spacing to be large. Then if you have few spacing, then you should use the spacing of your graph. Then the next thing I need to explain is the answer. So the correct answer according to the software is something close to 2.566, whereas mine is 2.3. So this software will not grade you if you are not 95% close to the correct answer. But the reason why I should not bother about this is the computer answer is based on the fact that we have other factors like internal resistance and all of that. So that's where this answer is coming from. But it's still very close to what I eventually got. But one thing you should notice, your answer should be close to 2, no matter what the case may be. So then let's take a look at the correction. The correction here, this shows the answer for the second question. So in case you noted your answer, so the answer here is 249.9. This brings us to the end of the physics experiment. You can download the Mavinhub Physics Lab from our website and practice this experiment until you are confident about it.